In our last 3 lessons, we talked about different conformations of the same molecule and constitutional isomers. In this chapter, we'll talk about stereoisomers, which are isomers with the same connectivity but different orientation in space. We're going to focus on the subset of those that are configurational isomers, which necessarily have different orientations in space, as opposed to the conformational isomers that we had talked about before. These can be divided into the very similar enantiomers, which are mirror images of each other, and diastereomers, which are configurational isomers that are not mirror images. If we put that into the context of this flowchart that we used before, we are going to talk about this central thread of isomers that are connected the same but are still different molecules. We're going to start with enantiomers. If molecules have mirror images that can't be placed on top of one another, which we call non-superimposable, then they are considered to be chiral. If you look at the dancing couple and try to think how they'd line up with their mirror image, the woman's arm and the man's arm would both be on the wrong side. In a mirror image, things that are farther out from the mirror on one side are just as far out on the other side. So the man is farther away from the mirror in reality and also in the mirror. Likewise, the OH that is pointed out from the mirror and the OH that is pointed into the mirror in the molecule shown are both farther away but in opposite directions than the other atoms shown, which are all in the plane of the mirror. The mirror images themselves are called enantiomers. They are 2 different stereoisomers because they are at least one part of them is pointed differently in space. The most apparent enantiomer relationship is that of your left hand and your right hand. For most purposes, they are identical, but they could never fit into the same baseball glove because every finger is pointed in exactly the opposite direction. On the other hand, mirror images that are superimposable, meaning they can be placed on top of one another and be identical, are not different molecules at all. Molecules like this are called achiral. This would be more like one of those one-size-fits-all stretchy gloves. You can just as easily put it on your left or right hand, so achiral. Most of the time in organic chemistry, something is chiral when it is a tetrahedral atom with 4 different things attached. You can see that if you have any of the same group, like in the top 2 rows of this figure, the molecules could be rotated and laid on top of their mirror images. When you try to do the same thing with the molecule in the last row, the molecule cannot be laid on top of its mirror image. Try to envision rotating to get any 2 atoms into the right spot. No matter which 2 you line up, the other 2 will always be swapped. This is the main way that we see stereoisomers come up, but we can also see them come up as cis or trans isomers. They're stereoisomers, but they are not necessarily chiral. In the next slides, we'll walk through drawing the enantiomer of a molecule. We'll start by drawing the original atom next to a line that will serve as our mirror. Draw the atom at the center of your 4 different groups on the opposite side of the mirror, the same height along the line and the same distance from the line. Repeat with one of the lines that is in the plane of the paper, not wedged or dashed, and the atom at the very end of this bond. You'll do the same thing with the remaining atoms as well. Every bold wedge in the original model will become a bold wedge in the opposite direction. Every dashed line will become a dashed line in the opposite direction. Once the molecule is drawn, try to envision rotating around the carbon-hydrogen bond to line up the fluorine of the mirror image with the original molecule. Notice that the chlorine and bromine are swapped when you do this. Being able to identify whether a molecule is chiral or not is an important skill. Generally, we will just draw the mirror image and see if we can rotate the mirror image to match up with the original. For this molecule, we cannot, so the molecule is chiral. We can also determine if an individual atom, usually a carbon, is chiral. We can simply count to see if 4 different things are attached to the atom. When an atom is chiral, it is called a stereocenter. Sometimes the differences that make something chiral will come after the first atom attached. Any difference anywhere down the line still makes the molecule chiral. Take, for example, the carbon nearest the top of the molecule shown in black. It is attached to chlorine, a hydrogen, which is not shown, a CH to the left, and a CHCl to the right. Even though there are two carbons attached, those carbons are attached to different things, making the original atom still a stereocenter. It is important to be very careful when looking for superimposability. The molecule as drawn here seems chiral until we rotate around the carbon-carbon single bond. The mirror image is still the same molecule after rotating around the carbon-carbon bond, and now is clearly superimposable. Remember, we can always rotate around single bonds with some limitations in rings, but we cannot rotate around double or triple bonds. We also need to look for chair flips that allow our mirror images to line up. However, things are much more straightforward for this type of analysis with Haworth projections. A plane of symmetry can also be a quick way to recognize chirality or symmetry in an object. If a mirror plane can pass through the object and leave the two sides as reflections of each other, the molecule is symmetric and therefore not chiral. If this is not possible, then the molecules are chiral. Stereocenters, or chiral centers, can also be a good indicator of chirality. That's why they're called chiral centers. Any stereocenter could have two possible orientations, which we'll learn to label as an R or S in our next nomenclature lesson. Generally, the presence of a stereocenter indicates the entire molecule will be chiral, with the exception of mesocompounds, where the chiral center can itself be mirrored across a plane of symmetry. The stereocenters can still be labeled, but the overall molecule is achiral. There are some limited examples of molecules that are chiral without a single stereocenter. These usually occur because the geometry is constrained, like in a molecule with two pi bonds on the same carbon. Because these pi bonds need to be using different p orbitals from the central carbon, they need to be at right angles from each other, creating kind of an extended tetrahedron. If you think about it, this arrangement of atoms is necessarily the same as the arrangement of electron pairs around carbon dioxide. So carbon dioxide should also have its lone pairs rotated in the same form. Other atoms besides carbon can also be stereocenters, with some caveats. Nitrogen has a lone pair that can be considered one of the four groups, but it costs only a small amount of energy to unhybridize the non-bonding electrons of nitrogen, which can then rehybridize to make either enantiomer with equal likelihood. We call an equal mixture of enantiomers a racemate, spelled R-A-C-E-M-A-T-E, racemate, and the process of making them racemization. However, if a nitrogen has four alkyl groups attached, it will no longer be able to unhybridize, and so can hold a permanent stereocenter. Sulfur can also have four different groups attached, like in the S-adenosyl methionine, SAM, an important biological cofactor that delivers methyls. Sulfur can also racemize, since one of those groups tends to be a lone pair, but it happens slowly enough that S-adenosyl methionine can last and be useful biologically. The relationship between enantiomers is that of exact mirror images, so enantiomers are always going to have the exact same physical properties. Diastereomers, on the other hand, are not mirror images and so have a relationship that's more similar to that between constitutional isomers. The formula is the same, but properties are completely independent. Generally, diastereomers will have multiple stereocenters, and only some of them will be inverted, while enantiomers will have all of their stereocenters inverted. Think of it like this. My hands are enantiomers and can catch a ball equally well. For my hands, not well at all. However, if we flip some of the stereocenters on a hand, say attach some fingers in the opposite direction, now we have a hand that has completely different properties. It would be impossible for such a hand to catch a ball. We also describe a special kind of diastereomer called an epimer where only one stereocenter is flipped. In our example, it would be like flipping just one finger. The only reason this is important is because it helps us to describe a close relationship between stereoisomers that may be interconverted biologically. For example, alpha and beta D-glucose are epimers that are readily converted back and forth because only one stereocenter needs to be changed. Here are two examples of diastereomers. The top is a set of diastereomers with the relationship I just described. Multiple stereocenters, but only some of them are inverted. The bottom is the other instance of diastereomers that we most commonly see. Cis and trans isomers relative to a double bond. It is worthwhile revisiting our chart now that we've defined all types of isomers to see the differences in those relationships. First, constitutional isomers are kind of like cousins. You may see some similarities, but there might not be much resemblance. Conformational isomers, on the other hand, are more like clones, as they are the same molecule. Diastereomers, again, have no close relationship between properties. They have the same functional groups, so there will be a slight family resemblance, but not necessarily much. Maybe like siblings. And finally, enantiomers are mirror images of each other, like identical twins. These molecules are indistinguishable from each other except in very particular circumstances, like around other chiral molecules. A great way to think about the way enantiomer properties work is your feet. Like your hands, your feet are mirror images of each other. If you put a sock on your chiral foot, since the sock is achiral, it makes no difference which foot it goes on. However, your shoes are chiral, so when your chiral feet interact with your chiral shoes, they will have very different properties, depending on which shoe you choose for which foot. Sometimes the change in properties is somewhat predictable. Alkenes give a great example of this. Every one of the alkenes in this table is an isomer of the others. The main difference between these isomers is how many carbons are attached directly to the double bond. Compare trans-hex-3-ene and cis-hex-3-ene. The trans diastereomer has a lower heat of combustion, indicating that it is more stable. So trans alkenes are more stable. Now take a moment to note the trend in stability as we move from monosubstituted to tetrasubstituted. Pause and make sure you try to identify this yourself. Notice that the monosubstituted hex-1-ene is far less stable than the tetrasubstituted 2,3-dimethyl-but-2-ene. So we see that substitution increases overall stability. Now back to this chart one more time to think about separations. Constitutional isomers and diastereomers can be separated like any other molecules because they have completely different properties. But enantiomers only act differently if they're around chiral molecules. This means that to separate enantiomers, we need to have a special chiral method. We might crystallize alongside a chiral salt or run through a chiral column, but we can't separate these out using conventional means. The very first chiral separation was done by hand, or by tweezers, I suppose, by Louis Pasteur, of pasteurization fame, who recognized that two different crystals formed from sodium ammonium tartrate and then proceeded to separate them one by one. There's one other way in which chiral molecules are different, and that's how they behave when exposed to polarized light. Remember, light is electromagnetic. When light is polarized, its magnetic field is all going to be in the same direction. Ordinary light has electric and magnetic components in all directions, but we can pass that through a polarizer that selects for only electric fields and magnetic fields in one set of parallel planes. Because the light and the chiral compounds both have magnetic fields, the chiral compound will cause the light to rotate. Because enantiomers are mirror images, their interactions with polarized light are equal in magnitude, but reversed. The amount that any solution rotates polarized light can be measured by turning a second polarized filter to let the maximum light through. Whatever angle is measured will follow a similar relationship to the Beer-Lambert law. There will be a measured value that's comparable to absorbance, and that measured value is set equal to the specific rotation, which we can compare to molar absorptivity, times the length of the cell, times concentration. Again, remember that each enantiomer will rotate in equal magnitudes but opposite directions. If a solution is racemate, each enantiomer will cancel out the others, so no optical rotation will occur. Any rotation would indicate an excess of one enantiomer over another. Clockwise rotation is called dextrorotatory and is indicated by a lowercase d or a plus sign. Counterclockwise is indicated with a lowercase l or minus sign, indicating levorotatory. We can determine how much of one enantiomer we have in excess of the other enantiomer by comparing the observed rotation to the ideal value. This, as a percent, is called enantiomeric excess. While we are on the topic of polarized light, light can also be circularly polarized, which can interact with repeating patterns of structure found in proteins differently. The three types of secondary structure found in proteins have specific ways that they interact with circularly polarized light, and these three responses can be modeled to the spectrum of any protein to determine how much of a protein is each type of secondary structure. This process is called circular dichroism.